Gas Chromatography by Raghib Rahman and Jessica Kim. Gas chromatography, or GC, is a quantitative method that is used for separation of volatile organic compounds in a given sample. Separation occurs as a result of a unique equilibrium established between the solutes and the stationary phase, or the GC column, and an inert carrier gas carries the solutes through the column. A gas chromatograph generally has a variety of different parts. However, it usually tends to have at the very least an injection port, a carrier gas, a detector, an oven, a column, and they are all usually connected to a computer. Uses of GC. GC tests the purity of a particular substance and is very sensitive. It separates the different components of a mixture and determines the presence of trace elements or compounds. How it works. A GC generally consists of a metal outer column with a coated stationary phase. A sample consisting of one or more compounds is injected into the column and is carried by atmospheric air, which is the mobile phase. Organic compounds flowing out of the chromatography column are indicated as a peak on a chromatograph. The unique time it takes for a specific compound to exit the column after it is injected is called the retention time. Because retention times are unique, when using a GC, a compound can be identified from a mixture based on the peak it displays. There are three parts to the process of using a GC. They are calibrating the instrument, injecting the sample into the chromatograph, and measuring the standards and unknown samples. The first step of GC usage is to calibrate the instrument. This is done by turning on the GC and making sure that it is connected to your computer, and adjusting the settings to appropriate temperature and pressure for device warm-up. To do this, after connecting your GC to your computer, start the data collection program. Then choose New from the File menu and bring up the temperature-pressure profile. Set the temperature and pressure values to appropriate settings for your experiment. Select Done to initiate GC warm-up. When the GC is ready for injection, it will read Inject and Collect simultaneously. It is imperative to not inject your sample prior to this message appearing. Sample injection, while seemingly simple, is actually very complex. It is usually done with a special type of syringe. The syringes are usually cleaned with methanol and wiped with a chem wipe. To do this, depress the plunger and submerge the needle into a vial of methanol. Pull back the plunger to fill the barrel about halfway through with methanol. Expel the liquid onto a chem wipe and repeat the previous step about 2 to 3 times. Wipe down the syringe and then flush it with your sample. After flushing the syringe with your solution, submerge it and draw about 0.1 microliters of liquid. Inject this into the GC to begin data collection. The final stage of GC is the measurement of standards and unknown samples. After the sample is injected into a stream of an inert gas, usually helium, that acts as a carrier, the gas stream moves at velocities that are influenced by the degree of interaction of each component with the stationary non-volatile phase. Substances having greater interaction with the stationary phase separate from those with smaller interaction. Various peaks will appear for mixed compounds. Singular peaks will appear for pure compounds. Retention time will dictate the identity of a compound. Area under peak will dictate how much of an analyte is present.
The chemical constituents that are being identified and measured, otherwise known as analytes, in GC should be organic, inorganic, and must be volatile. The dynamic range of GC varies. However, the range is usually between 25 femtograms and 100 picograms. But we have to keep in mind that it depends on the materials that are being tested, as well as the type of detector that is being used. Standard deviation or noise. Noise is unwanted information that reduces the accuracy of a reading. Noise can be caused by a variety of factors in GC. However, the most common cause is typically a contaminated injector or a column. Sample preparation. It is important to make meticulous measurements when preparing your sample. For example, the process of submerging the glass syringe's needle into the methanol acts as a blank injection process that flushes possible contaminants out of the syringe needle. For optimum efficiency, the sample should not be too large, and the injection should be quick to avoid band broadening of unresolved peaks. Accurate injection is crucial as solutions tend to evaporate in the needle. There are a variety of problems that can occur during GC. Sample problems include using non-volatile substances, which will ruin the expensive chromatography column, and calibration, incorrect temperature values of the GC instrument. Injection volumes should take into account the temperature of the inlet and the type of solvent being used. There can be a considerable difference in the gas volumes generated by different solvents when a sample vaporizes after injection. And finally, excess volume of a sample injected into GC. If the sample volume injected into the GC is too large, it can result in errors and peaks. Since most chromatographic samples are only a microliter or less, accurate measurement is difficult. Automatic injectors and sampling valves can reduce this error to a few %.